50 Shades of Visual Studio. I'll be speaking about an experimental project of mine where I try to visualize differences in binaries that were introduced by Visual Studio optimization settings. This talk is a mix of analysis of optimization settings, of visualization techniques, of binary call graphs, of call graph visualization, of threat detections, of metrics engineering. So it's a very colorful mix of different topics. Throughout the slides, there's a lot of numbers, and that occasionally might be very confusing. And I know that confusing things tend to be boring, so I put a lot of try to put a lot of funny pictures into the slides to keep people awake from passing out on my numbers. First of all, starting the talk with a disclaimer. That just disappeared. There it is. This is possibly the ugliest slide I've ever put on any of my PowerPoint decks. To be honest, I copy-pasted that slide from my manager. I recently started work for Intel, and I work on Rodrigo's team, and Rodrigo told me to just copy-paste this disclaimer here. So here it is. I don't speak for my employer, all the opinions and information presented here are my responsibility, and obviously I do not work for the Intel Security Group or McAfee. All right, that said, let's go on with the actual topic. So my name, as just introduced, is Marion Marschalek. I spent most of my professional career in threat detection. I worked in antivirus. I worked for an advanced threat detection company. I worked in incident response. So I did it all, and just about 8 weeks ago, I left that field to start work on low-level security, as just mentioned, for Intel in Portland. And if Intel ever happens to give me business cards, I will ask them to put my job title as Graph Dracula, because just last year I fell madly in love with binary call graphs. And this is what this current project of mine is also based on binary call graphs. Where does this come from, though? So over the past year, I've been working on IOC engineering. IOCs are used for threat detection. IOC stands for Indicator of Compromise. And if you've ever worked with threat intelligence data, you'll find out that most of the IOCs that are currently shared for threat detection are MD5 hashes and SHA-256 hashes, which is possibly like the most stupid way to try to detect malware on an infected system. I think classical antivirus has stopped using MD5 for threat detection about in 95 to 98. And now with threat intelligence, we go back to the stage where we came from and use file hashes again. So I've been working on several projects, one in cooperation with the National Cert in Luxembourg. The National Cert in Luxembourg is operating a threat intelligence sharing platform called MISP, Malware Information Sharing Platform, or something. And we have tried to come up with new ideas of how to develop indicators that are more resilient to change in binaries and that are cheaper and easier to produce than indicators that we currently use. There was one of the projects to integrate the graph analysis tool that I actually presented about here last year into the MISP threat intelligence platform to be able to create more resilient indicators. In the second project, I worked with a researcher from the University of Cambridge where we tried to measure the resilience and the cost effectiveness of indicator creation. And now, in this talk today, I want to explore how resilient threat indicators are if different compiler settings are used in binaries. That sounds a bit odd, but in fact it can be very helpful to be able to use the same kind of indicator for the same kind of source space that has been compiled into different projects. If you ever looked into optimization settings, if you use the same source code in context of different source projects, source code might end up looking different in the compiled binary in the end, which for threat detection is a problem if you use metrics that match for exactly the piece of binary or piece of code that you try to detect. All right, so yeah, what we're actually working on is we try to create more indicators because we're not satisfied with all the hay that we already have, so we need more hay. But how does the hay look like? Most of my professional career, as mentioned, I worked in threat detection, and that's a rather frustrating field because threat detection is suffering from one and the same problem since basically the creation of threats and threat detection. Threat detection in its basic means is either file hashes or file fragments or behavior or other properties of files that we can use. It's system behavior or network patterns that we search for. It's anomalies. It's known bad and known good and non-known bad and non-known and whatever. So it's all data that basically suffers from one and the same problem, which would be that it's all heavily building on known fragments. So we need a file to create that file hash to detect that file, or we need the actual behavior to search for on our system or in the network stream that we're scanning. And this all tries to find largely unknown pieces. It's true that threats or threat actors reuse code and they reuse techniques, but in the end, the mass malware market, as I would call it, relies on changing patterns consistently to evade detection, which is based on repetitive fragments. And this, in my opinion, is mostly the problem that the metrics that we're using aren't smart enough to actually adapt to the changing binary surface that we try to detect. So what we tried to come up with was smarter indicators, as I said, that were more resilient to little changes in files and that were more adaptive to how threats would change over time. And we built metrics out of the file geometry, the graph geometry. We tried to engineer metrics out of APIs found in binaries, out of behavior gadgets that were found within the API structure of a binary. And we also built metrics around strings found in binaries. So this is all formal research. It's been published about half a year ago. You can look that up on my GitHub. So later, and in the end, it will all be, hopefully, sooner or later, incorporated into the MISP sharing platform. And what I've been working on for a presentation here today, as I said, was try to look how these indicators change if I recompile binaries with different optimization settings. The tool that I've been using, that I've been speaking about for a long time now, is R2Graphity. It's based on Radar2. It's a binary parser which creates the call graph out of a compiled binary. The call graph would be all of the functions of the binary and how they interconnect with calls and jumps. The most important components in these call graphs are the function nodes and the function edges, of course. And over time, this graph structure has been fitted with lots of other attributes. By now, the graphs are humongous, so there isn't actually all the information about those graphs on the slide. Again, I would recommend to look up former presentations where I spoke in more detail about how the graphs actually look like and which information they provide. I'll be speaking a little bit more about attributes of these graphs that were used for the compiler settings optimization a little bit later during this presentation. Again, yes, I still use Radar2. I still have lengthy conversations about why I actually use Radar2. If you ever tried using it, you've probably found some frustration in it's difficult to use and the commands are hard to figure out, and Radar2 is still full of bugs. I'll admit that. But the benefit that I found in using the tool was that A, it's open source. I can scale it. I can run one instance of it. I can run 20 instances of it, and I still don't have to pay money. And the second point would be that it's actually a really elaborate framework around a good disassembly engine. So Radar2, I'm pretty sure right now is using the Capstone 2 disassembly framework, or the disassembly tool. And the framework that's built on top of it is the most elaborate that I could find in any open source or freely available disassembly tool. So that's why. I'm also still working with the Radar team to try to fix their bugs, and I'm fixing my bugs, and we're having a happy, very fruitful cooperation there, I would mean. Also, still static analysis is king, or in my case, rather princess. Why am I living on static analysis? I've also had lengthy discussions about this. I don't believe in sandboxes, just to say that. Because just imagine whenever you put a file into a sandbox, it means that there is a virtual user doing a virtual double click on that file, and that file is expected to, at any point in time, in there show all of its behavior, which is never going to happen. This is why I don't see why an entire industry is working on sandboxes and sandbox behavior, feature extraction, machine learning, and whatnot, because I think it's just not working properly, which is why we go static. What I mean with static, the tool that I worked on basically disassembles the whole binary file, or that's what Radar is doing, disassembling the file, trying to detect functions, and then translating these functions into the call graph. So every function becomes a node, and every call becomes an edge, and this is how we get a graph. That's a beautiful thing about binaries, they're naturally call graphs. They're bound to be call graphs because this is how they're structured by nature. Call graphs, yo. The beautiful thing about looking at a call graph is that in the ideal call graph, so given that Radari does its thing right, and given that the R2 Graffiti tool does its thing right, we have the coverage of 100% of the file, so we can see all the functions and see how they interleave. This, of course, has limitations because function detection in binaries in this assembly framework is still a hard problem and doesn't always work so well. And also other issues like C++ or indirect function calls, etc., is giving us a challenge. But the basic chance of getting higher coverage with static analysis is a lot bigger than with dynamic analysis. Also, these graphs are a lot more resilient, while the problem on the other side is the parsing complexity. Executing a file on a sandbox is a lot faster than trying to create a proper call graph of the binary. How is this working? The whole tool is based on Python 3. It's using Radari 2 and R2 pipe for disassembly. It's using network X for creating the actual graphs, and PIFA and PyDeep and NumPy for generating metadata and calculating the metrics out of the file. Also, there is a rather in-functional connector for Neo4j. So in theory, the whole binary graph can be translated into a database and can then be created in there. But therefore, Neo4j has to be set up on a proper machine and maintained properly. And I eventually gave up developing that branch because Neo4j is just so upsetting. However, we still have the call graphs. As mentioned before, function detection in disassembly frameworks is a hard problem. This is something that, as of today, I learned out of discussion with other reverse engineers is an unsolved problem. And even elaborate tools such as IDA Pro have their problems with it. Also, there is a little agreed on method to verify whether a detected function in a disassembled binary is actually a true positive or a false positive. If you look at IDA Pro is very good in function detection. The IDA Pro developers have also spent significant time and significant resources in improving their disassembler. I'll give them that. But occasionally you will still see how a jump table, for example, is disassembled into bytecode, or how strings are interpreted as executable code, or how executable code is interpreted as strings, and so on and so forth. So this is not actually an easy challenge. On this slide, you see a comparison between R2 and the just mentioned other function count. It turns out if you poke the R2 people about how they compare to IDA Pro, they get rather tipsy about that. So I called the other tool just the other tool. And comparing the function count, one can see that Radari 2 in some occasions finds a lot more functions than IDA Pro, which in most cases, as I found out, were false positives. I might want to mention though, if you look at the call graph of a binary, a wrongly detected function will not actually appear as a part of the graph, but as a part of a disconnected function because it's never called, because it's not an actual function. So in the case of the call graphs, finding too many functions isn't so much of an issue as finding too few functions, which is why I can still safely use Radari 2 for my call graph project. I tried this comparison first on Windows 8 system files, benign files, and on another set of malicious files. And it turns out malicious binaries are a lot more homogeneous in how they look in their binary structure than benign files. Which got me interested in why this is so. As a reverse engineer of malware, after a few years of looking at binaries, you'll find out that you keep seeing the same things all over again and again, and that they all look the same all over again. Which in my opinion is mainly due that malware authors, well, first of all, most of them use Visual Studio. This is fairly clear. So I'm a reverse engineer of Windows malware, which is very accustomed to Visual Studio, and whenever I see a GCC compiled binary, I get nervous because it looks so awkward. So there's this one part, and the other part would be that malware authors, in my opinion, use very little of what Visual Studio has to offer in optimization. So most of the binaries really just look structured the same, the stack is built the same way, variables are assigned the same way, registers are used the same way. So over time, as a malware reverse engineer, you get very accustomed to that. And then if you start looking into compiler optimization settings, you get some horrible experiences in how binaries can actually look like if the optimizer did its thing on the binary code. So this is how this started. The whole tool, I might also mention that the parser has its corner cases and issues, as every open source tool, I would think. For one, there is a problem with C++, because C++ has a lot of indirectly called functions that aren't easily parsed, because they aren't necessarily called by their offset, but well, indirectly by calculated offsets. I also have a big problem with Visual Basic and .NET, but then again, who doesn't? Delphi is also still an issue. I also still hate Delphi like the pest, and other exotic compilers, yada yada, again and again. Large binaries are an issue if you, like me, run the parser on an Ubuntu virtual machine with limited memory and limited capabilities overall. And of course, also loops and inner programming logic of binaries are an issue, because if you look at the call graph, you can't actually easily look at the inner logic of the function itself. All right, now what do I mean with those optimization settings that I promised to speak about? If you've seen my talk from last year, you might remember that slide where I poked at a very simple source base compiled with different versions of Visual Studio and different compiler settings. And then I realized when I visualized those graphs, they look different, naturally, because an optimizer on the binary call graph does terrible things, as mentioned before, which is why we end up with these different call graphs as shown here on the slide. The problem there is, as mentioned before, if you generate threat detection metrics that rely on a certain representation of the source code, we might end up only detecting one compiled version of that same source base. It's not that common that malware authors realize that their optimization settings or optimization settings that they use actually alter or actually hinder threat detection. But it is very common that source bases are copy-pasted. For example, my favorite case is SUSE, which is probably still copy-pasted into new versions of banking trojans. And as soon as code is copy-pasted in a different context, in a different source project, it will most likely change its representation on the binary level, just because the optimizer runs its algorithms and reorders and restructures instructions, functions, and basic blocks. So how can we build metrics that work its way around these optimization settings? Let me clarify in this talk also, I'm not a specialist on compilers. I skipped that class at university because I thought it's boring. That was one of the biggest mistakes I did in my life, I'll admit. Optimization by itself is a huge topic that you could probably speak about for an hour or more just by itself. So I kept the chapter rather short and will refer you to a very nice book that I found, which is called Engineering a Compiler, 2nd edition by Cooper and Thorson, where you have an entire chapter of about 100 pages of how optimization works. Important to know about optimization now is that it has different scopes. So an optimizer of a compiler will look at the instruction level within basic blocks. It will look at regions within instructions, which usually is loops or specific parts of a function. It will look at the global function. This is the most confusing scope because it's called global, but it only looks at the function. And it will look at interprocedural dependencies, which means how functions interact with each other and how they should be laid out in the binary. What an optimizer basically tries to do is make assembly more intelligent. If you look at a binary that's compiled without any optimization settings, you will see things like calls to APIs like string length twice in a row, where the result is then stored into a register and then used for an operation, and then string length is called again, and that same value is being stored in the same register and being used again. And this is something that the optimizer tries to find and eliminate because it's useless to generate, to calculate a value twice in a row if you could just store it in a register or a local variable. So reuse of previously computed values is a big point, but also the ordering of instructions within basic blocks to enable instruction level parallelism to help the CPU execute faster. Loop unrolling, if a loop is only called a couple of times and not like hundreds of times, it makes sense to just copy the loop body several times after each other in the binary to enable faster execution. The order of basic blocks and the order of functions within the binary is relevant for faster execution because there's things like jumps and calls that eat up a lot of resources at runtime. So as much jumps and calls as the optimizer can save, the faster the binary will execute. And of course, inline substitution of functions is interesting if we talk about very small functions. We can eliminate a lot of calls by just copy pasting the actual executable code of a function into the binary code to save time on the call. And this, as mentioned, just a very short summary of what optimizers can do. Again, I recommend reading the book. It's very interesting. And this is about everything that I ever know about optimization settings. The same thing, by the way, goes for the visualization. I like to play with visualization, but I'm not an actual expert on it. But what I do know as a binary analyst is that optimization settings can do terrible things to binary code, which makes it sometimes more readable and sometimes a lot less readable. But most of all, the different settings alter the code in a way that it doesn't appear in the same binary representation anymore. This is just one example that I screenshotted out of one of the case studies that I used. On the right side of the screen, you can see the very optimized version of the binary. So here I applied all the optimization settings, and on the left side you can see the version without any optimization settings. In that zoom in that I put on the slide, you can see that there's a lot of interaction with the stack. So local variables here are used for storing and loading values again. And turns out this is a very slow operation, so the optimizer decided to use registers just instead of the stack variables. This is a very simple form of optimization. Others will look a lot more complicated, especially if we talk about arithmetics and numeric calculations. My favorite case of optimization settings that freaked me out in the past was a piece of malware that was used, that was compiled to use up as much space as possible. This helps for faster execution at runtime, but also it blows up the binary incredibly. So in this binary, a lot of functions would be inline, which means a given function would grow in its size because subfunctions would be inlined. And as an analyst, you then end up analyzing that same code over and over again. Because you don't have one function to analyze that you can rename, but you see that same function inlined in the actual executable code and have to analyze it again and again and again. This much about the reverse engineering pain. So what did I actually do to visualize those optimization settings? For my experiments, I used 3 different case studies, which are listed on this slide. One of them is codenamed Win32 Window. It's a simple Win32 window application. All of the case studies are rather small, so the source space is approximately the same size, which doesn't mean that the binaries that turned out were about the same size. But anyway, so the code names are Win32 Window, RandomNG, which is a C-based random number generator, and LongPrimeC, which is a C++-based prime number generator. These are just random source projects that I downloaded from the Microsoft website. I went to download stuff from the Microsoft website because it turns out if you take those projects and load them into Visual Studio, they will just compile without any issues. I tried the same thing with malware, so with leaked malware source code, and turns out they aren't that easily compiled because whenever you find the wrong version of Visual Studio that was not used for writing this code, well, let me just put it, malware authors aren't actually that good in aligning their code with different versions of compilers. For the experiment, I used only one version of Visual Studio, which was Visual Studio 2015, and I listed the different settings that I used on this slide. As I mean settings, these different binaries that I produced only ever used one of those optimization settings that are listed on the slide, so I codenamed them in their respective compiler flag. And one version of each respective binary was compiled with all of those settings together. This is like the most extreme form of optimization. Optimization that Visual Studio uses is hilariously underdocumented. So if you go to MSDN and look up those optimization settings, MSDN will explain to you what the terms mean that the name of the setting contains, but nothing more. So there isn't actually so much to find out about Visual Studio's optimization settings just from the documentation. The basic objectives that the compiler can follow in terms of optimization. Would one be size? We can produce very small binaries. It would be speed. We can produce very fast binaries, which generally results in a bigger code base. And we can produce code that uses as little resources as possible, which resources would mean either memory or registers, which then results also in rather big and bloated binaries. Now dance, my case studies. Dance. What are we looking for if we look at compiler optimization settings in terms of call graphs? So from the data structure that I generated out of the graffiti tools, what we can look for is, for example, node counts and edge counts. The size of the graphs will change as we use different optimization settings. The number of jumps and calls and numbers of different other instructions, or like the count of generally used instructions, will vary. The variance of instructions within the basic block and within an actual function will change. As if you think, for example, in loop unrolling or function inlining, if you copy-paste the same source code a lot in a given function, the general variance of instructions within that function will go down. And we can also look at data references and memory references and instructions that perform these references within the function. And finally, how do we look at that? So this was the experiment that I conducted that tried to visualize those changes within the binaries. And as it turns out, I've done binary visualization before. Binary visualization by itself can sometimes be pretty, but it's not always that useful. Binaries can be visualized in a lot of different ways, but if you try to visualize the binary code, you should need to know what you want to see in the visualization beforehand. Otherwise, it turns out to be pretty useless. This is a dot graph of a rather large binary, and as you can see, if you visualize this graph in a dot version, it's not helpful at all. So how can we make the visualization more useful? First of all, if you start visualizing, don't think about it as an application of artificial intelligence, because visualization will highlight the things that you want to find in the data, but you need to be aware of what you want to find before that. It's also always helpful to reduce the data to the actual part that you want to visualize and to simplify the data, because otherwise, as mentioned, you end up with graphs like this, like huge and humongous. How to pick the features for visualization? First of all, you need to know what your tool can produce. You can't visualize things that aren't actually present in your data. You need to know what your algorithms support, like which algorithm to use for visualization, which tools, and what your data can provide for you. And finally, what I found out about binary call graphs is that, of course, graphs are beautiful for visualization, because in their natural structure, they are actually already something that looks pretty if you put it onto a PowerPoint slide. Therefore, I used the dot graphs that I talked about last year, and force-directed graphs, which is a more visually appealing visualization technique for graphs. I used heat maps for highlighting data and differences in data. I used histograms and diagrams and distributions for showing the changes in the data. Now, which attributes are the ones that I added to the graph structure in order to visualize compiler settings? For once, the total appearance of different types of mnemonics within the binary were a super interesting thing to look at. Also, as mentioned, the variance of mnemonics in dedicated functions, the presence of different instruction families, and how this presence would change when applying optimization. As mentioned, the graph node and the edge node, because naturally graphs would change with different settings, the total API count, and maybe even the total count of string constants, that's not listed here, the total amount of data references within the binary, and calculated metrics like ratios that abstract the total count of a given item by the size of the code section of the binary, and also variance and standard deviation of the mentioned attributes to see how much the binaries would change in total. Now finally, the data. I promised you there would be a lot of slides with numbers, and then we get to those numbers. On this slide, you see an example of the total count of mnemonic types within one of the case studies, which would be the prime number generator. And if you look at that, you will see that this is not actually very helpful. So this lists the total count of appearance of different types of instructions within the different binaries. As you can see them listed here in the top line of this data. This is actually hard to read. Yeah, don't try to read the numbers. In the top line is the most optimized version of the binary, and at the bottom is the least optimized version of the binary. And you can see that some of the numbers, some of the columns change a lot, and some of the columns change a little. And this is easiest to be seen when applying heat maps. You cannot read the numbers again, but look at the beautiful colors. These are the three case studies as compared to each other. Like each of the colored columns is a different family of instructions, and you can see that some of those columns are very homogeneous. So these numbers don't change a lot as different compiler settings are applied. And some of the columns show different colors, which means they change when applying different settings. And these are the columns that we're actually interested in for having a closer look at why they change. And also comparing different source bases when we realize that the C version, or the random number generator written in C, shows different changes than the C++ binary or the window application. Some of the interesting instructions that I picked out for visualizations with other techniques later would be call and jump, of course. Any kind of conditional instruction, like conditional jumps or conditional moves. The compare instruction, anything that has to do with function stack management or function management, like the return instruction, the push instruction, and the pop instruction. So these were the columns that showed the most differences in numbers, which is logical. If you have a lot of function inlining, for example, a lot of pushes and pops and returns will be optimized out of the binary and will not appear in the heat map anymore. A different way of optimizing, of visualizing this would be to look at a given case study and look at the number series that were produced for the different instructions. So here we get a lot of differently colored lines which represent the different families of instructions that are visualized. And you will see one particular instruction that is a total outlier in this data set, which would be this red line that goes in steps up and down there, which is the move instruction. So apparently for the random number generator, when applying different optimization settings, it makes sense to use a lot more move instructions, which in the end will probably save calculations. Also what is interesting, of course, the version of the binary that was applied with all of the optimization settings, of course, shows the lowest numbers in this graph, and the version of the binary with the least optimization settings, of course, shows the highest amount of instructions in total. A different form to look at this, as mentioned before, if you look at the heat map and pick the instructions to show the most differences, you can look at those instruction families in more detail, where histograms are very helpful. In this histogram, you'll see that the conditional jump and the call instruction were the ones that were most used within the binary, and that also show the most variance over applying the optimization settings. While this is nice to look at and interesting, in the end it's not actually that helpful. For binary visualization, or for the visualization of changes within a binary, I'm still a big fan of using directed call graphs for the visualization of the overall graph structure. In this graph structure, we see highlights for the jump instructions, as this instruction family turned out to be the one that showed the most changes throughout the experiment. And I tried to highlight this with yellow. So the more yellow a dot is, the more jump instructions it shows, and I see that the beamer is eating up those colors as well. But have a short look at the subgraph that the gray arrow on the right side is highlighting. This is a subgraph that appears in the binary with the least optimization settings, and you can see how in the binary with the most optimization settings, the subgraph is just disappearing. It's being incorporated into the larger graph base. One issue that I faced with the case studies that I picked is that the graphs were rather small, and the smaller the code base, the least changes the optimizer will apply naturally. So the visualizations don't show massive differences between the optimization settings. What we can also do in this visualization now is to look at the actual numbers. And if you look at the numbers of jump instructions within that code, you will see that there's kind of a major node or a master node in the version of the binary with the least optimization settings, where, the main node shows a total of 20 appearances of the jump instructions, and this node or this number is just disappearing with different kinds of optimizations. Furthermore, a side experiment that I performed when looking at instruction counts was trying to look for algorithms within the binary. This kind of lies at hand if you look at the random number generator project. You will see that there's a lot more arithmetic instructions showing up in the source space, which is logical. And if you use that information and try to highlight the use of such instruction families in bigger source spaces, you end up with something that pretty much works as an algorithm detection. This was just a side project where I tried to find the compression algorithm that has been incorporated into a piece of malware named Babar. So if you try to look at arithmetic instructions, try to highlight those in call graphs, you can actually be able to spot numeric calculations, in this case the compression algorithm that was copy-pasted into that malware. Well, this has nothing to do with optimization settings, I just thought that the graph was pretty. What you can further do when looking at the count of instruction families in binaries is try to make it more comparable by abstracting it to a distribution of variances of given instruction families within the functions. So I tried to generate a distribution of the variance of instruction families within functions, and it turns out there is differences to see between the different optimization settings. For looking at the variance, one has to define bucket sizes for the given variance numbers to be able to make the numbers comparable among the different binaries. What's nice about these distributions is that they're actually resilient to little changes. So if our source code changes, the representation of the numbers does not, because we still have the same amount of buckets and the same amount of numbers that we put into those buckets. This will be the data and how it looks like. Again, don't try to look at the numbers, but try to look at the visualization of those numbers. So let's look at a couple of distributions. Again, this is like the base set of numbers that I produced. In this case, again, for the prime number generator, the bucket sizes are varying because it turns out the numbers or the distribution isn't actually as equal as would be beneficial for visualization. So I redefined the bucket sizes and went in smaller steps in the beginning, from like 0 to 5 to 10 to 50 to 100 to 250 to 200. And then scaling that up to an amount of 10,000. As you can see, the smaller buckets on the left side show a high number of functions that are present within those buckets, which generally gives us an idea that the overall variance of instructions within a given function is rather low. At least when using Visual Studio, you will see that the total amount of different instructions within the binary isn't all that high. You can probably count, if you count the different types of instructions, you will end up with like 30 or 40 different instructions. And if you've ever seen the Intel manual and the amount of instructions that are documented in there, you will feel rather stupid just knowing 30 different instructions. That's just as a side note. But yeah, so the overall variance of instructions within functions isn't all that high. These kind of number series can be visualized again in a diagram as shown here. And one will see that for the prime number generator, the variances aren't actually that far off. So the numbers don't change all that much. We see gaps as big as about 20 functions in and out that change within the buckets. If we look at the different series though, we see that for the random number generator, those differences are a lot higher or a lot more visible, especially in the bucket number 2 and bucket number 4. And finally, if we look at the last series in the visualization of the Win32 window, we can again see that the bucket number 4 is the one with the highest peak, which for me means that the bucket number 4, which I think was between 200 and 250 or something, is the amount of variance that's most present in compiled binaries overall. What is also quite visible though is that the window application doesn't show so much difference at all when applied with different compilation settings. So you will see that most of those lines align with each other, and there isn't actual spikes of differences between the settings. Which I would conclude that an application that's heavily relying on or in this case on the Windows system of Windows, or like of the Windows API, or in general relying very much on the API of Windows for any kind of purpose, shows less success or less changes in optimizations than programs that don't use the API all that much. This is because larger Windows API calls are actually very hard to optimize out of the binary. If you use the runtime a lot, this can be worked on by the optimizer, but the actual API calls to the Windows API are very different in their appearance in the binary and very difficult to optimize away from the actual source code. So this will be why we see so little changes in this case study. Numbers. The visualizations are interesting to look at. I like to stare at data, I like to stare at the visuals, but you will see that with those graphs, you can make your conclusions, but they aren't actually feasible to use for any given use case. I started off the project because I was curious, I'll admit that, and I found the use case for that project a little later on. And now here comes the actual use case. So all the visualizations are based on numbers extracted from the different binaries. And these numbers tell us things. They tell us how the binaries change. They also tell us in how abstract we would have to generate our threat detection metrics to be able to still detect code that has been recompiled with different settings. And this is where I actually wanted to get it. Comparing the different optimization settings in terms of numbers does only make sense if those numbers aren't bound to different source spaces. So in order to find deviations of the optimization settings, we have to look at the same source space, which is kind of logical. Also, as I keep being asked as I work on binary call graphs, no, I still don't diff binaries. I just like to compare numbers. Also on the slide, there is a long list of attributes that were used for the comparisons that I will be speaking about in the next slide, which would, for example, be the file size or the code section size, and see how these change with the different settings. The total amount of local references within the binary, the total amount of API calls within the binary, the total amount of data reference counts and ratios calculated with function sizes, and the amount of API calls. And then 3 different attributes that count particular calls to given APIs that appear very frequently within Windows binaries. And the idea here is to look at how these attributes change when looking at one given source space. And that wouldn't look like that. Very pretty, again, lots of numbers that you probably, again, can't read. So what I tried to do is look at all of these different metrics and see how much they change when I apply different settings in order to be able to tell whether these attributes serve as proper metrics to detect threats that have been, or to detect malware that has been recompiled with different settings. So the idea here was to find out how much these attributes vary when applied with different optimization settings. The source space where these attributes varied the most was again the random number generator in C. I would suspect because there is very little APIs and very little strings appearing in this binary and a lot of arithmetic calculation. This is my theory, and this is why this source space, or the metrics for the source space within the space of the compiled binaries that I looked at changed at about 30% on average, so between 5 and 30%. While when looking at the window application, where as mentioned, a lot of Windows API calls are being used, the changes would not be any higher than 4%. So we look at changes of 30% versus 4% when looking at these different source spaces. The prime number generator showed changes of about like 10 to 15% for these metrics. For me, in threat detection, that would mean if I use these attributes for generating my indicators of compromise, I would have to acknowledge for a deviation of my metrics from about between 5 and 30% to be able to still detect the same source space with this kind of indicators. The numbers that are presented on this slide aren't always to be trusted. I also found that out because there's one that shows a standard deviation of 346%, which is only the reason because it changes only by 1 bit. So the largest amount of this metric would be 1 and the smallest amount would be 0, which is like a huge change of 100%, which in reality isn't actually the case. So these numbers have to be taken with concern. Why? Why did I do this whole project? Why did I try to build those metrics? What's the whole point of it? If you've seen my talk last year, you might also have seen this slide. I've decided to make this my standard conclusion slide for every kind of talk that I'm giving on threat detection metrics. Why is this whole project useful? I've been talking a lot about metrics. Let me get back to the metrics. First of all, one of the points that I figured would make sense to look at optimization settings is because with the metrics extracted, on the one side, we can try to detect which optimization setting was used for a given source space. And on the opposite side, as mentioned, we can generate metrics that are oblivious to those changes. So first, if we look at the changes that actually appear within our metrics, we could potentially be able to detect which setting a binary was, with which setting a binary was compiled. Again, here's a large dash of numbers. Again, you will probably not be able to read those numbers, but just consider if you look at the different attributes that are listed on the slide, like for example, the total count of functions divided by the size of the code section, or the total amount of jump instructions divided by the code section, or the total amount of calls to get proc address divided by the size of the code section. We get indicators that help us compare different source bases and their different and their optimization settings. So here we're looking for numbers that differ a lot between different optimization settings, and we can use this delta between the indicators to try to define which optimization setting was used for a given source space. This is probably more useful in a future project because the source spaces that I had were only 3, and I would probably need a couple of hundreds to be able to derive proper indicators. So this is still future research to be done. On the other side, if we're not interested on the changes, we can look at the similarities, where comes my last case study I'll be talking about today. If we look at a different set of source spaces, namely actual malware code compiled with different optimization settings, we could try to see how much our indicators have to differ to be able to still catch the same malware. There's something I've been talking a lot now and for a long time. I'll do this very quickly. So I went to a GitHub repository, which is listed on the screen. It's hosted by a user called fdiskq, whatever that means. And he keeps collecting malware sources. So if you ever want to do compiler research on different malware source spaces, this is the website to go to, or the GitHub account to go to. And from there, I downloaded 3 different source spaces that I compiled with Visual Studio 2017. Again, I use pretty much the same optimization settings to generate different binaries from these source spaces. And again, I can say that's my case studies dance. So let's see how these pieces of malware change. Here are going to be a lot of slides with a lot of numbers on there. Again, don't try to look at the numbers. I just wanted to mention I looked at these 3 different pieces of malware. at their file geometry, which would be attributes like the file size or the code section size, or the different sizes of all the sections in the binary, or the entropies of those sections, like static data that you can generate from the binary geometry for the 3 different case studies. Then the second category will be the graph geometry, where we look at the binary call graph and look at the function count and the edge count and the count of different API calls and the misses in API calls and the strings that are referenced and different ratios that are calculated, and try to compare those for the 3 case studies. And finally, API level indicators, which would mean how many calls there are to get proc address, how many calls there are to create thread, how large are callback functions within the binary, how much do thread handlers change within the binary, what's the average path length within the graph, what's the shortest path length. Like if you look at NetworkX, it offers a lot of algorithms to extract features to help describe the graph, which in our case here could be variable thread detection metrics. Finally, for the metrics, I also looked at the strings contained in the binary. You can evaluate strings by how often certain characters appear within that string and evaluate how meaningful or how much information is contained within a given string. And that can also serve as a thread detection metric. For all of these numbers, again, I calculated the standard deviation to measure how much these indicators change when different optimization settings are applied to the source space. And the findings in this experiment were that for malware source spaces, like the average malware, that's not heavily relying on Windows APIs because there is no GUI being created, there is no heavy network stack, there is no massive interaction with the operating system, as you could see in a benign file. We see an average deviation of about 15%. So if you look at those indicators presented and abstracting by 15% of their total value, we can have indicators that are able to detect the same malware compiled with different optimization settings. Finally, yes, this project is supposed to be productive. It's supposed to be integrated with the malware information sharing platform of the Cert of Luxembourg. This is an ongoing approach. As I recently started a new job, the approach is going very slow right now. But in the end, what we want to achieve is to generate threat detection metrics that are cheap to produce. We want a short parsing time, we want a simple parser, we want the metrics to be easy to deploy, and we want the cost of the metrics to be the minimum, so we don't have commercial tools to extract them, but only open source and simple setups. We want the metrics to be scalable, so we want the features to be easy to extract and to be easily adapted to new challenges in malware. We want them to be resilient against little changes in the binary, as for example would be a change in compiler settings. And we want them to be reliable, which is currently the biggest problem. As mentioned before, Radari 2 is, well, getting along, let's put it like that. The parser that I wrote on top of it was written by me and not by a software developer. So Russ is trying to fix bugs in there. And as soon as we have the whole parsing system at the level where you can say we have reliable data, we can finally start extracting meaningful detection metrics. Because we really don't like the classical threat detection. All right, that was it with my talk. Thank you very much for your patience and your willingness to look at a lot of data with me. If you have any questions, I'm happy to answer them now. Otherwise, thank you very much for your attention and have a happy break. Thank you.